Ask a current model how many R's are in strawberry. It'll get it right. Now ask it about a word it has never seen, one you just made up. Watch it get that wrong. The famous strawberry failure got patched, but it got patched the way you'd patch a symptom, not a cause. The cause is still there, it's still shaping every answer you get, and it has nothing to do with the model being bad at counting. The model literally cannot see the letters. This isn't a quirk. It's the first thing that happens to your text, before any attention, before any layer, before anything people normally make videos about. And it silently explains a pile of behavior you've probably filed under AI is weird. Why non-English languages used to cost up to 9 times more per message, and mostly don't now, why a single leading space can turn one token into 3, why models are strangely bad at rhymes and anagrams, why a handful of specific strings used to make GPT-3 produce total gibberish. By the end, you'll be able to look at any of those and say exactly which stage caused it, and you'll understand why nobody has just fixed it. Here's what actually reaches the model. 10 characters, that's what you see. The model sees 3. Sint raw berry, not 10 letters, 3 chunks, and look at the middle one. The model doesn't see 3 separate R's scattered through a word. It sees a chunk that happens to be spelled raw as one indivisible unit. It doesn't even see them as text. Each becomes a number, an index into a lookup table. That's the input, 3 integers, and each of those integers pulls one row out of a very large matrix, a row of numbers, every one of them learned during training. Here is what one of those rows actually looks like. Roughly 4,000 numbers, none of which mean anything on their own. That is the vector for the chunk, raw. Not a symbol the model looks up in a dictionary, a single point in 4,000-dimensional space, and everything the model knows about that chunk is smeared across those 4,000 coordinates. Stack all 3 together and you have the real input, a matrix, 3 rows tall and 4,000 columns wide. That matrix is what the transformer receives. The letters are gone, discarded before layer 1. And here's how thin the ice is. Add a single space in front of the word. Same word, 1 leading space. 3 tokens becomes 1. A completely different input, a completely different vector for what you and I would call the same word. So when you ask how many R's, you're asking a system that never received letters to count letters. It can only answer if, somewhere in training, it learned facts about the spelling of those specific chunks, which it does learn, for common words, because people write about spelling on the internet. That's why strawberry works now and your made-up word doesn't. It memorized the answer for one and has no letters to count for the other. Now the obvious question, why on earth would you throw the letters away? Let's try to design this ourselves. 2 options look reasonable. Option 1, feed it characters. 1 letter, 1 token. Nothing is discarded, spelling is trivially available, no vocabulary problems at all. This works and it's used in some systems, but look at what it costs. A 2,000-word document is maybe 3,000 tokens under the normal scheme. As characters, it's around 12,000, call it 4 times longer. And attention cost scales with the square of sequence length. 4 times the length is 16 times the attention cost. So character level isn't wrong. It's just expensive enough that you'd rather spend that compute on a bigger model. Option 2, feed it whole words. Short sequences and each token is meaningful. Better on length. But now, how many words are there? English has hundreds of thousands in common use, and that's before names, typos, URLs, code identifiers, and every other language. Your lookup table becomes enormous, and most of it is rows you'll barely ever train. And then someone types a word that isn't in the table. You have no representation for it at all. For a system that has to handle arbitrary text, that's fatal. So we're squeezed from both sides. Characters, sequences too long. Words, vocabulary too big and still breaks on anything new. We want short sequences and a bounded vocabulary and the ability to represent literally any string. Here's the move. Don't decide the units in advance, learn them from the data. Start with characters, so anything is representable. Then look at your whole training corpus and find the single most common adjacent pair. Merge it into one new unit. Repeat a fixed number of times until you have as many units as you want. That's byte-pair encoding, and notice what falls out of it for free. Common words become single tokens because they got merged early and often. Short sequences. Rare words stay split into pieces, but they're still fully representable. No unknown token ever, because you can always fall back toward characters. The vocabulary size is a dial you set. You stop merging when you've hit your budget. Nobody sat down and decided strawberry should be 3 pieces. It fell out of how often those character sequences co-occurred in the training corpus. The tokenizer is a compression scheme fitted to a specific pile of text, and everything strange downstream follows from that one fact. So, stated generally, a tokenizer is a learned map from strings onto a fixed vocabulary. It is constructed by greedily merging the most frequent adjacent pairs in a training corpus, and the procedure halts once that vocabulary reaches a target size, for current models, typically between 30,000 and 200,000 entries. Text goes in, a sequence of integers comes out. Each integer indexes one row of the embedding matrix, a matrix carrying one row for every entry in the vocabulary and one column for every dimension of the model. Each of those rows is a learned vector. Those vectors are the first thing the transformer ever sees. 2 consequences worth sitting with. 1. The tokenizer is frozen before training starts. It's fitted first, then the model is trained on top of its output. Changing it later means retraining the model. This is why tokenizer quirks are so persistent, they are load-bearing. 2. The merges reflect whatever corpus the tokenizer was fitted on. Text that was common in that corpus compresses well. Text that was rare does not. That asymmetry is baked in permanently, and it is not neutral. Back to the cold open. The model can't count letters in your invented word because the letters were merged into opaque chunks before the model saw anything, and there's no memorized spelling fact to fall back on. It isn't bad at counting. It's answering a question about data it doesn't have. Now the other things you can explain. Why some languages used to cost several times more and mostly don't now. This is the part where I have to correct something you've probably heard, including from other videos on this exact topic. The claim is that non-English languages cost you 3 times as much. That was true. It is largely not true anymore, and the reason why is the most interesting thing in this video. Same sentence, translated, measured across 3 vocabulary sizes. With a 50,000 entry vocabulary, the standard around 2019, Burmese took 9.3 times as many tokens as English. Thai 5.4. Hindi 5. Same meaning, 9 times the cost, 9 times the context window consumed. Double the vocabulary to 100,000 and Burmese falls to 6.4. Take it to 200,000 and Burmese is 1.7. Hindi is 0.9, fewer tokens than English. Russian and Thai land within 10% of parity. Nothing changed about those languages. What changed is the vocabulary budget, and crucially, the extra merges were deliberately spent on non-Latin scripts. Today's frontier tokenizers sit at 200,000 and above, Gemini's runs to around 256,000. The inequality was never a property of the languages. It was a consequence of how a compression budget got allocated, and when people pointed at it, it got allocated differently. Which tells you the thing worth actually remembering. The tokenizer is a design decision, and design decisions have politics. Somebody chose. It could have been chosen otherwise, and for Burmese speakers, that choice was a 9 times tax on using the technology at all. Why a trailing space changes the output. Hello and hello are usually different tokens with different ID, not the same word with a modifier. Different row of the embedding matrix, different vector, different everything downstream. Why rhyming and wordplay are oddly hard. Rhyme is about sounds, which come from letters. The model reasons over chunks. It can learn which chunks tend to rhyme, but it's working at secondhand from something it can't directly inspect. Why solid gold Magikarp broke GPT-3. Some strings appeared often enough in the tokenizer's corpus to earn their own token, but were nearly absent from the model's training data. So the model had an embedding row it had essentially never trained. Feed it that token, and you're reading out near-random initialization, and the model produces nonsense. A glitch token isn't a bug in the model. It's a seam between two datasets that were assumed to match. What I simplified. The real thing operates on bytes, not characters. That's the byte in byte-pair encoding, and it's how any Unicode string is representable at all. I also showed merges as a clean loop. Production tokenizers add pre-tokenization rules that constrain merges across whitespace and punctuation. And the exact splits differ from one tokenizer family to the next. The GPT line, the llama line, the gemma line. Tokenize the same word with two of them, and you get two different answers, which is exactly what you saw a moment ago. And byte-pair encoding isn't the only way to build a vocabulary. The alternatives differ in one specific thing: how they decide what belongs in it. Word piece, which BERT uses, doesn't merge the most frequent pair. It merges the pair that most raises the likelihood of the training corpus, a subtly different criterion that sometimes picks differently. Unigram works backwards. It starts with an oversized vocabulary and prunes the entries that explain the least, which is what T5 and Gemma use. And one worth correcting, because it's routinely listed as a fourth algorithm. Sentence piece isn't a rival algorithm at all. It's a toolkit. Its trick is treating the input as a raw stream with spaces included, so it needs no language-specific pre-tokenization, and then it runs byte-pair encoding or unigram inside itself. Then there's the option of no vocabulary at all. Feed the model raw bytes and let it learn its own structure. That would make this entire class of problem disappear at a compute cost people are still arguing about. The next one is about what happens after this. Those vectors go into attention, and that's where sequence length starts costing you real money. Next video, attention built from scratch, not described, derived. We'll start from each position needs to look at the others and let Q, K, and V fall out on their own.